Welcome to A-Level and AP Physics. In today's lesson, we will discuss all possible graph questions from gravitational field and simple harmonic motion. We will discuss these questions in detail as always we do, so you can improve your conceptual understanding of gravitational field and simple harmonic motion. And also you can have better understanding of graph questions from these two topics. Let's study together, let's improve together. Question 2, part A says, state the relationship between gravitational potential and gravitational field. This question is very common in past papers, and also this concept is very important to answer past paper questions from this topic. Let's try to understand how these two quantities are linked with each other. We can simply say g as a function of r, this is equal to negative dv by dr. dv by dr, this is simply gradient of, this is representing gradient of v against r graph, mean potential against distance graph from the center of massive object, gradient of v, and this is the negative, so we can say, so g is equal to negative gradient of vr graph. And the meaning of negative sign is very important. What this negative sign is telling us, negative sign means that g is, or you can say g points towards decreasing potential, very important one, points towards decreasing potential. Which way potential is decreasing? G is directed towards that direction. So you can also simply understand with a very basic example. This is, let's say this is a sphere, this is a massive object. If you look at this point, if we go up, potential will increase. So I will say if we go up, potential will increase. But if we go, potential will increase. But if we go down, potential will decrease. So it means that g is, direction of g is in direction of decreasing potential. A beautiful point. Later you will see the importance of this with the help of graphs. Now let me show you how you can write down the answer for this question. For the answer of this question, simply you can say gravitational field equals negative gravitational potential gradient. Means you take the gradient of v against r graph and add negative to that. That is the value of g. Part B says a moon of mass capital M and radius capital R orbits a planet of mass 3m and radius 2r. At a particular time, the distance between the centers is capital D, as shown in figure 2.1. Point P is a point along the line between the centers of the planet and the moon, at a variable distance x from the center of the planet. The variation with x of the gravitational potential phi at point P for points between the planet and the moon is shown in figure 2.2. Simply graph between potential against distance is given to us. Part B1 says explain why phi is negative throughout the entire range from x is equal to 2r to x is equal to d minus capital R. Means from this point to this point, why potential is always negative. This question is very common question. They will ask you this question in many different ways. So you need to clear your concept how to answer this type of problems. Let's try to understand this one with one very simple example. We can imagine that we have one capital mass M. This is mass capital M. And now you can also imagine that we have one test mass. So let's say this is one small test mass. So this is test mass. And we can also assume at infinity. So here we can define infinity. At infinity you need to understand that we take potential is equal to 0. Gravitational potential at infinity is 0, and electrical potential also we assume at infinity is equal to 0. Because in physics potential difference is defined but potential is not defined. That's the reason we assume a reference point. So we always assume this is as our reference point, mean infinity. So if potential is 0 at infinity, it also means that at infinity GPE is also 0. Now imagine that if we move this mass up, is the separation between these two objects, is it increasing or is it decreasing? So you need to understand in terms of separation. As separation is increasing between these two masses, I hope you will say GPE is also increasing. Now assume the same test mass at this point. Now this is moving down. Now is the separation between these two objects, is it increasing or is it decreasing? I hope you will say separation is decreasing. So if separation is decreasing between these two massive objects, it means GPE is decreasing. Now at infinity we have GPE that is equal to 0. That as object is moving down, GPE is decreasing. As GPE is decreasing from 0, it means this one has to be negative GPE anywhere from this point to this point. GPE has to be negative. So that's the reason GPE is always negative. GPE is always negative because at infinity we assume potential is 0 or we assume GPE is 0. So that's the reason potential is always negative other than infinity. For gravitational field we are talking about, but for electric field potential can be positive, it also can be negative. We will go to that point later. Now we need to understand why this GPE is decreasing, because in this case work is done by force, work is done by gravity. So work is done by gravity, or simply you can say gravity is an attractive force. Work is done by gravity, that's the reason GPE is negative, or you can say GPE is decreasing. So simply we can say in this case as test mass getting closer to the massive object, or we can say separation is decreasing from infinity, it means GPE decreases. So these points you have to write down in your answer. So let me show you the answer, how you can write down your final answer. So in your final answer you can mention these 3 points. One point you can say potential is 0 at infinity. We have already discussed that potential at infinity is 0. Second, you can say gravitational force is attractive, or you can say when work is done by gravity GPE decreases. So we can say this is the second point. The third point we can say as separation is decreasing. So this can be the third point. As separation is decreasing, GPE is decreasing. So these 3 points you have to mention in your answer. And this question is very common, so you have to master this concept. Part 2 says one of the features of figure 2.2 is that phi is negative throughout. Describe 2 other features of figure 2.2. So this is our figure 2.2. If you look at this figure 2.2, we can simply compare the potential at the surface. We can compare potential at this point and we can compare potential at this point. Potential here, this is more negative as compared with this potential. So simply we can say this potential here, phi is smaller. So the phi, the potential at surface of planet is smaller. If you look at the gradient at this point, and we look at gradient at this point, this gradient is also shallower. So the gradient at the surface of planet is shallow, and this one is steeper. So this one is steeper. And gradient we have already discussed that G is equal to negative dV by dr. So if gradient is greater, it simply means that G is higher. This negative telling us direction. So don't get confused with this negative. Negative telling us direction of G. So this is shallow and this is steeper. It means G at the surface of moon. So G at surface of moon, this one is greater than G at surface of planet. And the potential at the surface of the moon, we are just talking about the surface. As this one is more negative, potential scalar quantity. Potential is scalar, G is factor. So this negative is giving us direction of G. As this is more negative, it means G at the moon, this one is greater than means the phi at the surface of moon, this is greater than phi at the surface of planet, because potential at the surface of the planet is more negative, it means it is smaller. And also we can say about the point of maximum potential. So at this point potential is maximum, and this point is closer to the moon because this side is representing moon. On this side we have moon, on this side we have planet. So these are the points you need to understand. So we can talk about potential at the surface of planet, we can talk about potential at the surface of moon, we can talk about value of G at the surface of moon, we can talk about value of G at the surface of planet, and we can compare them. Potential is a scalar, as potential is more negative at the surface of the planet, it means this potential at the surface of the planet is smaller than the potential at the surface of the moon. As this gradient is less steep and this gradient is more steeper, it means that the value of G at the surface of the moon is greater than value of G at surface of planet, and the point of maximum potential is closer to the moon. So you can mention these points. We have discussed 3 points. We need to write down only 2 points. Let me show you the answer how you can write down this one in a proper way. And so simply one point you can say potential at surface of planet is smaller than at surface of moon, as we have discussed here. So this one point you can write down. Second, you can say potential gradient. Potential gradient means you're talking about G. At surface of planet is smaller than at surface of moon, as we have discussed this point here. And the point of maximum potential is closer to the moon. So this is point of maximum potential, we can say phi max. And magnitude of potential you can also say varies inversely with distance from center near the sphere. Near the surface it is inversely proportional to distance. So these points you can mention, very important points, you need to understand these points. Third part says on figure 2.3 sketch the variation with x of the gravitational field G at point P between x is equal to 2r and x is equal to d minus r. So for this question simply we have to sketch graph between G and distance, but we have graph between potential and distance. So simply we need to understand how potential and gradient, potential and G, they are linked with each other, means the relationship between these two quantities. We have already discussed that G is equal to negative dV by dr, mean this is negative potential gradient. Mean if we have the graph between V and R, simply we need to find the gradient. So the gradient of VR, this is equal to negative GR, we can say negative gradient of VR, this is equal to G. That's all. So simply we have to look at gradient of potential against distance graph. If you look at this gradient, this one is positive. So gradient is positive. So for the gradient I will be using letter small m. Gradient is positive. So G has to be negative. And if you look at gradient at this point, gradient is equal to 0 because this is horizontal, so G has to be 0. If you look at this part, gradient is negative, so G in this part has to be positive. Means after that G is negative, before this one G is negative, and after this one G is positive. And we need to compare the gradient at this point, and we need to compare gradient at this point. Now this gradient is shallow, we have already discussed this point. So this is shallow and gradient at this point is steeper. It means G at this point is greater as compared with G at this point. So in this case simply we can mark the point. So this point should be at low value of G and this has to be at higher value of G. So if we have these things in our mind, we can mark the points. We can mark this point first of all, then we can mark this point, then we can mark this point, and then we can sketch the graph. So let me show you how you can sketch a proper graph. And so this is how you can sketch a proper graph. So this point is very important. It has to be at lower value of g, and here we should have higher value of g. And the point where gradient is 0, this one has to be equal to 0. So this is how you need to sketch very important graph from this topic. Part B says, apart from the quantities in A, describe what may be deduced from figure 4.2 about the motion of the trolley between time t is equal to 0 and t is equal to 24 seconds. No calculations are required. So if you look at this given system, in this case, L is measured from this spot X. So if the trolley is moving to the right, L will increase. And if trolley is moving to the left, L will decrease. If you look at this given graph, we can see the initial position of the trolley is 25, mean L is equal to 25. Maximum value of L is 25 and minimum value of L is given, that is equal to 15. We have L on y-axis and we have t on x-axis. It means it is oscillating between two values of L, 25 and 15. As the initial value of L is 25, it means that initially we pull the trolley to the right. So we can say initially trolley is pulled to the right, so this one point we can write down, pulled to the right. So this is one thing we can deduce from here. And the second thing we can find out is, if you look at time period of this one, its time period is equal to 4 seconds. So we can say time period t is equal to 4.0 seconds. And also if we look at this motion, first part of the motion, this motion is undamped and this one is damped. So this is undamped. So we can also deduce from here. So this is undamped motion and this one is damped. This is damped. But this damping is light. So this is light damping because this is amplitude is decreasing exponentially and gradually. So we can say light damping. So we can say light damping. So third point we can say initial motion is undamped, means this part. Initial motion is undamped. And the fourth point we can say it's light damping. We can say after some time, after 12 seconds, we can say after 12 seconds, its damping is light damping. Its damping is light damping, or simply we can say after 12 seconds light damping. So in a simple language you can say after 12 seconds light damping. So it's easy way to write on. So we can say after 12 seconds light damping, means the motion is damped. And also we can conclude from here, at this point when t is equal to 0, it is at rest. But if you look at this point here, and if you look at this point, this is at 1 second, this is at 3 seconds. So this is 1 second, this is 3 seconds. We can say this is the equilibrium position. So this is very important one. So where is the equilibrium position? It is at 20 centimeters when L is equal to 20 centimeter. Equilibrium position is at 20, and at equilibrium position speed is maximum. So we can also say maximum speed. We can write down in a simpler way. We can say Vmax. So we can write down in a simpler way. We can say Vmax at 1 second, 3 seconds, and so on. And also we can say in this case stationary at, we can say stationary at, if we look at this point for example, you can say 2 seconds. It is also at rest at this point. We can say 4 seconds, 4/5, and it is also at rest at this point. This is also here, so 6 seconds and so on. Simply we can say so on. So you can see these points you can deduce from the given graph, and it's a very important skill how to read the graph. So you need to understand how to read the graph. So this is how you can read the graph. Now let me show you the proper answer written in a proper language. So this is how you can write down a proper answer. This is what you need to write down for the answer of this question. So at least 3 points you have to write down. 3 points. So but we have talked about 5 different points. If you mention 3 points, you will get 3 marks. Part C says on figure 4.3, sketch the variation with capital L of the velocity v of the trolley for its first complete oscillation. Before we answer this question, one thing we need to understand is that for this question it is given to us that V max of the trolley is 7.9 centimeters per second. This has been calculated in the previous part of the question, because in today's class our main goal is graph, so that's the reason we haven't done that part of the question. But Vmax is given to us, that is equal to 7.9 centimeters per second. So we have to sketch the graph between V and X, and V and X, they are linked with each other. V is equal to plus minus omega into a square minus x square, and X is the displacement, A is the amplitude. So this is the equation that connect V and X, and how V is changing with displacement from equilibrium. When X is 0, V will be maximum. So we can also write down V max, it is when X is equal to 0. So we will get omega times A, and this is at X is equal to 0, means when it is at equilibrium. So these points we need to understand. Now when we have this type of questions, we have to figure out first of all where is the equilibrium. In this case the equilibrium is at 20, means L is equal to 20. So we can draw the line here. So this is the equilibrium. So first thing we can write on here, equilibrium is at 20. So equilibrium is at this point, and it is oscillating between 25 and 15. So it is oscillating between these points. And also we have the maximum value of V, that is equal to 7.9. So here we have 10, 5. So it means each small square, this is equal to 0.5. So it means here we have 5. So here we will have 6. Here we will have 7, and here we have 7.5, and here we have about 7.9. And we can also mark here. So we have 5, here we will have 6, here we will have 7, and here we will have 7.9. So now simply we need to connect this one. So the shape can be circle, shape can be ellipse. It depends on the given axis. On given axis, scale, it depends on the scale. Shape can be circle or it can be ellipse. So let me show you the final answer. So if you connect these points, so this will be the shape of the graph. So this will be the shape of the graph. So it's better to write down the coordinates. So when V is maximum, when X is equal to 0. So we have maximum V here, we have maximum V here. And when X is maximum, speed has to be 0. Means when X is equal to a square, speed will be 0. So this is point here, speed is 0, speed is 0. So this is how you need to sketch a typical type of graph. You need to be clear how to sketch this. Shape is depending on the scale, very important. It can be circle, it can be ellipse. Part B says the resistance of the resistor capital R is increased. The magnet is again displaced a vertical distance capital D and released. On figure 7.2, sketch the variation with time t of the displacement small d of the magnet. So in this case resistance has been increased, so simply we can write down EMF, this is equal to I times R, and from here we can write down I, this is equal to EMF divided by R, and this I is the I induced. EMF is the same because initial displacement is the same. As resistance has increased, it means I will decrease. If induced current decreases, it means magnet loses less energy. Means less mechanical energy of the magnet decreases. Magnet loses less energy. As less energy is lost, it means that less damping. So simply we can say less damping, less damping, less damping. Simply we can say less mechanical energy has been converted into electrical energy. So it means less damping. If less damping, it means that d nu it has to be greater than d old, because amplitude of this magnet, or simply we can say displacement of the magnet, it will decrease less, because less mechanical energy of the magnet has been converted into electrical energy. As magnet is losing less energy, it means less damping. So the new displacement at any given time has to be greater than the initial displacement, or we can say the previous displacement, as shown in the curve. So now simply we need to sketch the curve, but time is the same. Time period does not change in this case. So this is how you need to sketch. So you can see at any given time, the red one, displacement is greater than the displacement of the previous curve. So displacement is greater. So this is how you need to sketch. This is how you need to sketch. Time period is the same, but only displacement at any given time is greater than before. Part C says the resistor capital R in figure 7.1 is replaced by a variable frequency signal generator of constant RMS output voltage. The angular frequency omega of the generator is gradually increased from 0.7 omega naught to 1.3 omega naught. Omega naught is the angular frequency calculated in A2. For part C1, on the axis of figure 7.3, sketch a graph to show the variation with omega of the amplitude A of the oscillation of the magnet. A beautiful question about resonance. First of all, it is given to us this resistor is now replaced by signal generator. So simply we can say here we have now signal generator. So this one is signal generator, variable frequency signal generator, variable. So I can mark this one here. So it's variable frequency signal generator, meaning the frequency we can change. Variable frequency signal generator. So we have variable frequency signal generator. So it will send alternate current, variable current to this coil, and this coil will produce its own variable magnetic field, and the frequency of the generator we can change. So it simply means that we can change the frequency of current, induced current, and also we can change the frequency of induced magnetic field. And this magnet, it has certain natural frequency. It is oscillating with a certain natural frequency. And when this become a magnet, at one instant they will repel each other. At another instant, these two magnets, they will attract each other, means there will be electromagnetic forces. And if we keep on changing the frequency at one certain frequency, when the frequency of the magnetic field induced in this coil matches with frequency of this oscillating magnet, means the natural frequency of this oscillating magnet, resonance will take place, and that resonance will take place at omega naught, means at this point it will take place, resonance will take place at natural frequency of this magnet. So we can say here resonance will take place because driving frequency will be equal to the natural frequency of this harmonic oscillator. So resonance will take place, and when resonance takes place, amplitude of oscillations will be maximum, and if we increase more frequency, it will start to decrease. And so these points we need to understand. So it simply means that this is now driven oscillator by electromagnetic forces, means by interaction between two magnets, or simply we can say between two magnetic fields. And this is a typical type of graph. Let me show you how you can sketch. So this is how you need to sketch this one. This is the initial amplitude of magnet. As we increase the frequency of the variable signal generator and its frequency is getting closer to the natural frequency of oscillating magnet, you can see amplitude is increasing. So here natural frequency of oscillating magnet is equal to the frequency of magnetic field induced in this coil, so resonance takes place at this point. If we increase more frequency, amplitude will not increase, amplitude will start decreasing. So this side has to be lower than, you see this amplitude is even lower than this one. So this is the initial amplitude of this oscillating magnet. So this point you need to understand. So this is how you need to sketch this curve. Let's try to understand a little bit more about this one. Here sometimes they will ask you to sketch curves like this. So this is when no damping. You can see amplitude is infinite, mean amplitude go on increasing if there are no resistive forces or if there is no damping. In this case, amplitude has certain value because this is not in a vacuum. There is air, so there are some resistive forces, so it has light damping. And then if we increase damping, you will see the time period, the frequency has shifted to the left. Mean frequency has been decreased, so with damping, time period increases. This one you no need to show in the previous part, the graph shape as we have sketched in the previous part, but for this type of graph you have to show that. And you can see even we increase the damping here, so this one has light damping and this one has medium damping. You see the frequency has decreased, it means time period has increased, time period of oscillation. And for heavy damping, you can see the natural frequency is here now, so the natural frequency decreases with damping. So this is very important point. So these points you need to understand. So this curve is very important one. So the frequency is decreasing. So let me draw the lines here. So you can see the frequencies here. Initial frequency, we have that one was here, and here you can see now. So these points you need to understand. So on these curves you have to show that time period is increasing with damping, but as we have sketched in the previous one, you no need to show that time period increase. We will assume time period does not change. Part B says, use your answers in A to plot on the axis of figure 3.3 the variation with displacement x of the acceleration A of the ball. So simply we have to sketch the graph between A and x. So we need to sketch a graph between these two quantities. So we need to figure out what is the relationship between these two quantities. A is equal to minus omega square x. Now if we compare this one with y is equal to mx, from here we can say m is equal to negative omega square. It means gradient is equal to negative omega square, or we can say omega square is equal to negative gradient of ax graph. So this is the point we need to understand. But from here we can also deduce that A is directly proportional to negative x. Very important point. It means A and x, they are directly proportional, but they have opposite signs. Means when this is positive, A has to be negative, and when this is negative, A has to be, when this is negative, A has to be positive. When this is positive, A has to be negative. Means when this is positive, this has to be negative, and when this is negative, this has to be positive. So the gradient in this case has to be negative, means the gradient of the line, it has to be negative. So let me show you how you can sketch the graph. Actually you no need to worry about the numbers, because these numbers we already have, we have calculated in the exam. These numbers will be given to you, but our main focus is on the graph, how to sketch the graph. So in the question it was given to us that when A is equal to x is equal to this one 1.7, value of A is equal to 5.2. So this has to be negative because this is positive, and when x is negative 1.7, A has to be positive 5.2. So it has to be a straight line, and the gradient of this one has to be equal to omega. Gradient has to be equal to negative omega square. So this is very important, and omega is constant, so gradient has to be constant. So we have discussed a lot of questions about simple harmonic motion, and also we have discussed one question about gravitational field. I hope if you have watched this video carefully, you have good understanding of these two topics. And if this video was helpful, please like and subscribe, because your encouragement is very important. See you in next video. And also, if you have any questions, please leave your questions in comments.